Thank you. Yes, thank you for inviting me. So today I will present you this paper that we wrote. So Alessio, with Alessio, Enrico, and Julian, who are the organizers of this very nice seminar series, and also with Eli Pomoni, who is my advisor. And so the broad topic of the paper, and of course this talk, is the thermal CFTs. So we can start with a gentle introduction of why we should care about thermal CFTs. So one of the main reasons is that if we want to understand or model quantum critical points and give an explanation of what is happening in the lab in terms of quantum critical points, then we really need to understand how to turn on the temperature starting from a CFT. Another reason is in the context of ADS CFT. Once we consider black holes or black brains in the bulk, then the CFT in the boundary thermalizes. And the last one, which is more general, is that if you want to study CFTs in backgrounds other than flat spaces, then this thermal geometries that we will consider are in a way the simplest next step. So then let me tell you what I mean by turning on the temperature. So of course, this is not the only way to do it, but this is the way we will focus on doing in this paper and in this talk, such that we consider a CFT in the flat background, and then we place the CFT on a cylinder, d-dimensional cylinder. And when we do this, we immediately introduce a scale to our theory, and this is the temperature, which is parameterized by the circumference of the compact direction in the background manifold. And when we do this, the conformal group is broken. So on the cylinder, the translations and spatial rotations are still preserved, but the dilatations, boosts, and special conformal transformations are broken. So this will drastically affect the form of our correlators. Yes. But still we have the translations and spatial rotations, so we will make use of them. And before going into further detail, I wanted to give you a general picture of where we are in the phase space, if you want. So the CFT sits in this blue point, that it's a specific point in the coupling constant. And then from this point onwards, we turn on the temperature and move away from this critical point in a vertical line in this diagram. So you should always keep in mind that we are starting from a CFT and moving away in a very specific way. Okay, so but when we place our CFT on this thermal cylinder, we still have a lot of information inherited from the CFT, and in particular the scaling dimensions and the coefficients of the 3-point functions are inherited from the CFT. So of course, since the symmetry group is broken, the form of these 2-point, 3-point correlators are different. But we still have these quantities, particularly as they appear in the operator product expansion. So this CFT data, we take it from the zero temperature, and we should also keep in mind that the OPE between two operators it's still a valid expansion. But of course, it's a valid expansion in a finite radius of convergence, which is given by the length of the thermal circle. So on top of the CFT data that we get from the zero temperature, now also some of the operators of our theory gain 1-point functions, and this is due to the breaking of the dilatation operator. But still, the form of these 1-point functions are very so we're very constrained. In particular, it has to be a constant, which we, for each operator that gains a 1-point function, we call it BO. And then we also have the contribution of the inverse temperature depending on the scaling dimension. So then, since now there is non-trivial 1-point functions for operators other than identity, we can use the OPE for the 2-point the thermal 2-point function, and we can expand a thermal 2-point function using the OPE. So in this case, this is something that we will extensively use throughout the talk. So I want to go over it in this expansion. We always have the OP coefficients. So OP coefficients includes the 3-point functions, the 1-point function, and the coefficients of the 2-point function in the 0 temperature. And then the rest is called, I will refer it as the thermal conformal blocks. And it's this factor and the Gegenbauer polynomial next to it, depending on the spin and the dimension of the operator that appears in the expansion.
Sorry, what is just the big J?
BTJ?
The big J. So we have C, new, J. What is the big J? Oh, like I never know how to pronounce this letter in English. I'm sorry.
So the J is the spin of the operator in the expansion. Nu is the D minus 2 divided.
So it's the J corresponding to the operator O as well as delta, and then you have delta phi.
Delta phi. Oh, sorry. No. So delta phi is the dimension of the external operator which sits in the 2-point function. So imagine that this is a phi, or imagine that this delta phi is actually a delta OI. So just the typo.
Okay, perfect.
Yes. And then on top of this, we also have a periodicity relation coming from the fact that we have a compact direction in our thermal CFT. And so the fact that we have a circle in the background tells us that every correlator that we will consider needs to satisfy this periodicity relation. And we will also make use of this extensively. And I should also tell you here that when we expand the 2-point function in OPE, the thermal conformal blocks are not manifestly KMS invariant. So there is a tension between them, which will be very useful for us. So now that I went through the basic ingredients of the thermal CFT, then I can pose the main question that we try to answer in this paper. So we asked how much can we learn or compute about the thermal CFT just by knowing the analytic structure of its correlators and the 0 temperature CFT data. And it turns out that we can compute quite a lot, and I will try to give you a flavor of this by, first of all, like restricting myself to the 0 spatial separation, and then I will present our analytic results. Then I will do again the complex tau plane formalism, but this time I will include numerical results also, and then I will generalize this setup and consider the non-zero spatial separation of 2 operators in the 2-point function. Finally, if time allows, we can also talk about a curious connection between the momentum space OPE. Okay, so again, we are thinking about the 2-point function, a thermal 2-point function of 2 scalar fields, but we are restricting ourselves to the case that the 2 operators are sitting on the same thermal circle. And this simplifies the OPE that I showed you drastically, such that when the spatial separation becomes 0, the Gegenbauer polynomials become constant, and then the OP coefficients, so the OP coefficients that appear in the expansion, includes the sum over these contributions of operators which have the same scaling dimension but different spins. And then, so we know the OP, and then we also know how should be the analytic structure of this two-point function in general. So we know, first of all, that when these two operators collide, when the distance between them is 0, then there should be a divergence. And then, since we have the periodicity, this pole should appear in the real tau line, separated by the distance of the thermal circle. So then, and there can be nothing more. So then we can consider complexifying tau and choosing a specific analytical continuation. And in this case, depending on the orders of the poles that appear in our two-point function, there might be cuts. But again, except these poles and cuts, there can be nothing more. And then once we fix the analytic structure, once we know that which type of analytic structure we are looking for, then we can play a very simple game and define our two-point function in terms of a Cauchy integral in a generic point. And then we can open this contour and make it infinitely big. And in this case, this contour will pick up all the poles, the contributions that are coming from the poles and the cuts. And then in principle, of course, there will also be a contribution that's coming from infinity, which we will independently talk. So once we open this contour, there are these contributions of the poles and the cuts that here I collect inside the piece of the two-point function that we call dispersion relation. And here, since there is KMS and all of these poles are identical, then we can compute the contribution of only one of these poles and cuts, and then we can shift this contribution in the real tau and get all the contributions. And here I should also mention that from here onwards, I set the length of the thermal circle to 1. So all of these poles and cuts are integer separated in the real tau. And then, okay, so this is the contribution to the two-point function that is coming from the discontinuity, and we call it dispersion relation. And then the rest of the contributions, which are coming from the infinitely big contour, is denoted as the arcs. And then, so once we have this formula, of course, if we knew the exact form of the two-point function, we could just compute the dispersion relation with it, but we don't know it in general. So then the idea was to use the OP to compute the contributions to the discontinuity for each operator that appears in the discontinuity separately. And when we do this, so the OP has a very simple structure, and then we can compute the discontinuity for each of these operators. And then we realize that for the operator that has this property that, like, if you subtract 2 delta phi from the scaling dimension, if this is even integers, then the contribution, so discontinuity doesn't pick a contribution from these operators. So here it is nice that then we know that especially in particular cases, which we will go through one by one, like a big portion of the operators that contribute to OPE do not contribute to the discontinuity. So the procedure gets simplified. But whichever operator that contributes to the discontinuity, we can just compute this integral and then sum over the infinite images. And once we do this, we realize that this the contribution of the dispersion relation becomes this two sums of Hurwitz zeta functions. And they are, of course, KMS invariant on their own. And then okay, so we should also add the arc contributions to here. So the conclusion of this discontinuity computation is the Hurwitz zeta blocks, let's say, for the operators that contribute to the discontinuity. And then we can also show separately that the whatever arc contributions that we were missing is only can only be a constant term. And then this is the description of the terminal 2-point function on the complex tau plane. And just to yes.
Can I ask a very quick question?
Yeah.
I'm trying to understand like the operator that drop out, because it's very counterintuitive. Does it mean really that like for some certain operators, like when they're going to come to the same point, they will not have a discontinuity in their 2-point function? Is that because you're saying you have to have this discontinuity because when you have two operators getting to the same point, you will have one in a field theory? Does that mean that these operators do not have that feature?
Now that this statement is true for the operators that contribute to the OP. So now that we inserted the OP.
Okay, yes. So that comes
so
up
then
in the
I am
sum
really talking about like specifically those operators, the contributions of those operators with their terminal conformal blocks. So it's not the statement about the external.
Okay.
Yes.
Okay, perfect. Now I understand. Sorry, thank you.
Yes. Okay, so then, maybe this was a bit too abstract, and just to give you a flavor, we can immediately do the example of generalized free fields and maybe understand it better. So the generalized free field is this one scalar field in the fundamental representation, and it should satisfy the equation of motion that is given here. And the D is the dimension of the space-time, and then the delta phi is the external, so that delta phi is the scaling dimension of this field. So in this case, we know the spectrum very well. So the OP of these two scalar fields can only have the identity contribution, and then all the double twists, and depending on the scaling dimension and the dimension. And then also, in this case, the exact form of the correlator is known. So once we do the computation, we can check it. And so if we insert the OP into this integral over the discontinuity, as I was showing you before, then we would see that this integral gives you this very simple expression. And if you set m to 0, if you want, this is the exact propagator that you would see in any way. And then what the prescription was telling us, that the dispersion relation, to get the full dispersion relation, of course, we need to sum over the images of this exact propagator. And then the result of the entire 2-point function becomes this one, so the sum of two Hurwitz zetas evaluated at the external dimension of the field. And now so this was a known result, and yes, so it agrees. But the point is now that you can see the form of the 2-point function in terms of the Hurwitz zetas. We can point out that the general formula that we obtain for the 2-point function is given in terms of a sum of GFF correlators, which was something that we didn't know before, and only when we can organize the 2-point function in terms of these blocks of Hurwitz zetas that are KMS invariant on their own, we can see that in the complex tau plane, that any correlator that we can think of in any terminal 2-point function that we can think of is given in terms of these Hurwitz zeta functions. And okay, so before going on to the other examples, I can maybe quickly summarize what was the prescription for this, so obtaining the time 2-point function. So first of all, we insert what should be the analytic structure of this correlator. And we should also tell the spectrum and the scaling dimensions of the operators. And once we input this, we can compute the dispersion relation using the OPE. And not all operators have to contribute to the discontinuity, which simplifies things drastically. And then we can compute the dispersion relation and get the final form of the 2-point function. And nicely, every 2-point function in finite temperature is given in terms of the GFF correlators. So another example, the next simplest examples can be given in terms of the ON model. So ON model is this theory that is defined, let's say, from 2 dimensions to 4, roughly. And so it is again this fundamental scalar, but this term with a quartic potential in the Lagrangian. And there are many versions of this theory that are interesting. So, for example, the first example that we would consider is the ON model in 4 minus epsilon dimensions. So, in this case, the theory becomes weakly coupled, and we can also do perturbation theory. The spectrum is very simple. Here I give you the first ones just to give you a flavor. And okay, so in 4 minus epsilon, we also famously have the critical point at lambda when lambda scales as epsilon. But then there are also other examples which we considered in different parts of this paper. So for example, when we consider the ON model in 3 dimensions, then the theory becomes strongly coupled, and one of the interesting famous examples is the 3D Ising, right? So then for the 3D Ising, the spectrum has the identity, then it has a sigma, so a field that I will call sigma in this talk, which is analog of phi and then epsilon. There's also another version of this theory that we are interested, and then for that one we again consider this theory in 3 dimensions, but then this time we consider a large N expansion. And then the spectrum of the theory becomes again the identity. There is phi, but then there is this other sigma field which is coming from the Hubbard-Statonovich. And this is also an example that we want to consider. So maybe, okay, so giving all of them at once was maybe a bit too much, but okay, we will use them. And in the ON example in 4 minus epsilon dimensions, the scaling dimension of the phi is given here. And we also know the anomalous dimension that comes to the phi square operator in the epsilon order. So then we make use of these 2 zero temperature data, and then again use our step-by-step formula to see which operators contribute among the ones that I give you in the beginning, which are, of course, the phi square, and then also the double twists of it. And in this case, we realize that in the 0th order in epsilon, only the identity operator contributes, which is not surprising because in the 0th order, the ON model acts like the free theory. And then in the epsilon orders, also now that phi square gains an anomalous dimension, on top of the identity, now the phi square operator also contributes. So then to compute the correlator in the epsilon order, we also need to include the contribution of the phi square. And here, just to give you a little flavor, so the free correlator was the one that I gave you for GFF, evaluated in the correct scaling dimension given here. And then the rest of the correlator that's coming from the phi square is this log contribution here. And then we, like, once we compute this, we can, of course, do the perturbation theory independently and check that indeed this is the result. And one last example for the complex tau plane is the ON model in large N. And in this case, as I told you, that we need to do Habar-Stratonovich to change the form of the Lagrangian, and then we can also take the large N. And at the end, so we have in our spectrum, we have the identity, which I didn't write here. We have the double twists, but on top of it, we also need to consider the powers of the sigma. And you might say, like, if you know ON a bit, maybe you are surprised that we will also consider the contribution of the sigma m, because in the zero temperature, it was the case that all the 3-point functions given with sigma m was scaling like 1 over n. So in the large N limit, these operators weren't contributing. But here we still have the same 3-point functions, but the 1-point functions of the sigma m's also scale like n to the power m divided by 2. So then the combination of these two quantities, which form the OP coefficients, they are in order 1, and they will contribute. And on top of this, this theory also has a thermal mass, which makes the correlators decay, especially in non-zero spatial separation. And this thermal mass is given by the 1-point function of sigma.
Actually, can I ask a quick question there?
Yeah.
It came actually quite belatedly. So you were saying that the only thing you impose is kind of this analytic structure in a complex tau plane. But don't you, in addition, have to impose this kind of thermal decay on whatever you get? Or do you know it will always be the case?
So we don't impose it, but at the end we expect it to have it. I will come to this point.
Okay.
And yeah, so it's true that the thermal decay should be there, but this is not something we impose from the beginning. So then, okay, so we do the same steps, but here the significant thing is that now that we have the sigma fields, then the contributions that are coming to the thermal 2-point function will be infinitely many. So identity operator will contribute. So phi will not contribute, and then all the sigma to the power m operators contribute. And then the thermal 2-point function is this infinite sum that if we stick to one strip in terms of tau, then we can also resum this infinite sum and obtain the thermal 2-point function in terms of 2 beta functions. And then the thermal mass that we were mentioning appears as a parameter in this function.
Can I ask a stupid question again?
Yes.
Can you go back one slide? So just to gain intuition a bit, because now it seems that since you always get like a sum about these free generalized fields, is that you kind of get a theory that looks a bit like a tensor product of free fields, but here you kind of have infinitely many of them. Is this kind of infinite sum reflect that you actually have an interacting theory, or do you also have interacting theories that have finite sums over these free theories?
Yeah. So yes. So it can also be only finitely many contributions and interacting.
Okay.
So maybe the point here is that a bit. So if you have a weakly couple theory, then most probably the operators that would contribute to the discontinuity will be less. But on the other hand, if you have a strongly coupled theory that also has scaling dimensions that are not integers or like not integerly separated, then almost all, maybe all of these operators would contribute. So there is a story like this behind.
Okay, perfect. Thank you.
Yes. So Now maybe I can again ask for questions, because now I will shift gears a bit and talk about the semi-analytic version of this complex tau plane. If there's any other questions. Okay, if not, so up to now I was talking about complex tau plane two-point functions, but I was talking about the theories that we know the CFT data analytically, but of course this is not the case for many other theories. So then we use the prescription we have, but then we also add numeric results to it to obtain other time two-point functions. But before going into the details of this, I want to quickly review this previous numerical way of computing OP coefficients. And so previously, Alessio, Enrico, Ellie, and also Julian was working on this method, and it starts with this observation that the time two-point functions that we consider, they are KMS, they have the periodicity condition. And this periodicity condition dictates the form of the thermal correlator in a very specific way. And in particular, combined with the OPE, we can see that around when tau is very small, when tau is very close to 0, the identity contribution in the OPE to the two-point function dominates. And on the other side, when you employ KMS and go to the tau very close to 1, then infinitely many heavy operators create exactly the same effect that identity operator was creating on the around 0. And this brings us a form of channel duality for time two-point functions that CFT 4-point functions would have, for example. And they were employing this channel duality to get the asymptotic description of the heavy of the OP coefficients of heavy operators. And so this asymptotic expansion has this leading term, let's say, in general, that is given here. And then by using this asymptotic form of the heavy OP coefficients, they were again using the KMS and the sum rules they derived to obtain the light, the OP coefficients of light operators numerically by solving the sum rules. And then they also knew that this asymptotic behavior of the heavy OP coefficients should be corrected, and the leading correction to this expression should come with 1 over delta being the dimension of the heavy operator. But other than that, it was nothing new, nothing known. And then now that we have this general description of the thermal two-point function, we can actually just expand this expression in terms of large delta and check if this is really the case. And of course it is the case. But now that we have the exact form of the correlator up to the OP coefficients, we can expand as much as we want and then get also the other corrections to this asymptotic behavior. And here I just give you a couple of them, such that now the coefficient that needs to come with this leading correction is given here, and then you can add as many light operators as you want and do the same inversion procedure and get the corrections in terms of also the scaling dimensions and OP coefficients of the other light operators. And by using the results that derived for the 3D Ising sigma correlator, now we can again do the same sum rule procedure, truncating the spectrum of the OPE in this 4 operators that we give here, and then instead of using OP or something else, we can now use the exact form of the Horowitz zetas that we derive here. And then, so this sigma correlator was computed by them, but also the Simons Duffin and his collaborators, and then we can improve the previous result. But I have to say that in this case, since sigma is a particularly nice operator, the improvement is not so much. So now the improvement is in the 10 to the minus 3 order. But a correlator, again, in the 3D Ising, that wasn't like possible to compute before with this procedure that I described, was the epsilon operator. And this is simply because if you go back and look at the asymptotic form of this expression, epsilon itself, the external dimension of the operator that we are considering, is so heavy compared to the operators that enter to the spectrum. The approximation that was given only in terms of the 1 over delta was not good enough. So this was not possible before, and now that we have the Horowitz zetas, we can do this. So this is the form of this should be the form of the 2-point function for the epsilon, and we also did Monte Carlo to check the result, and it's given here. Yes. Okay. So if there are no other questions, I will go and consider the case of non-zero spatial separation. Yes. Okay. So up to now, we only consider the operators that were on the same time circle. But now we can separate them, and they can be anywhere they want in the time circle. And in this case, we also know the analytic structure of the 2-point function. But first of all, I was always talking about the tau direction, which is the complex tau direction, which is the compact direction, and then the spatial direction was x, right? So I need to change coordinates a bit. So first of all, we can by using these 2 coordinates, we can define the z and z bar, and then from z and z bar, we can also pass to the r and omega, which is which is the useful way to think here, let's say. And then once we fix R and consider the omega plane, the analytic structure of the time 2-point function is given here, such that this poles in R and 1 over R are the poles that I was telling you before when the operators coincide. And then there are these cuts that between these points, and these are coming from the thermal blocks. And again, there cannot be anything more. And we can play the same game and use Cauchy integral to define the 2-point function. In this case, when we blow up the contour, we know that there will be this time these 3 contributions: the contribution around the origin, and then these 2 other contributions that are still in this x, the horizontal axis, and again there will be a contribution in the infinity. But the contribution that is around the origin, let's say, we can sum them into this one factor with respect to the discontinuity, and then we can just combine the kernels of each of these discontinuities into one kernel. And here you can see the explicit form of the kernel, such that the dispersion relation is given by the poles and the cuts around this horizontal axis. And then, of course, again, we have the arc contributions that we should take into account. So then we play the same game, and then we insert the OPE of OPE in the T channel. So OPE expanded in the let me say like in the right side of the thermal 2-point function plot. And one by one, we pick up the contributions of the operators that are in the OPE. And we can compute this. And then first of all, we should realize that the dispersion relation itself, when we sum over all the contributions of the operators, dispersion relation itself is not KMS invariant, which is not so nice. And on top of it, we can still expand the dispersion relation, so we know that we are not capturing the entire 2-point function, but we can still expand the dispersion relation part in OPE and then check if, for example, it satisfies OPE, if it has like more operators that we didn't put in initially, or if there is something wrong with it. And the point is it admits the same OP expansion, but the OP coefficients of the contributing operators are not the exact ones, but they only have the parts that are polynomially suppressed in J. And then we know that we are missing the piece of the OP coefficients that are exponentially suppressed in large J. And then, so we interpret this as, so from the OPE, the dispersion relation is only able to capture the piece of the OP coefficient that is in the OP regime, and we are missing the out of OP contributions, which we should somehow take into account. And I should also mention that this is also what happens in the Lorentzian inversion formula. If you would use the Lorentzian inversion formula to compute the OP coefficients, then again you would get the piece of the coefficient that is polynomially suppressed in J, in large J. And to take into account this out of OP coefficient, out of OP contributions, we have two methods in mind. So one, the direct one, is also numerical one, would be just to add this exponentially suppressed terms by hand that we know that we are missing with open coefficients, and use KMS, also add these coefficients and impose KMS in this way, so that you fix the coefficients that needs to come with these type of contributions. So this we did it for GFF and also the ON in epsilon expansion, because these are the nice examples that have like very little amount of operators contributing. And once we consider infinitely many operators contributing to the 2-point function, this method gets harder and harder. So the other way to take into account this out of OP regime contributions is to get inspiration from the form of the dispersion relation that was there for the complex tau plane, and sum over the images of the non-zero spatial separation dispersion relation, which by construction enforces KMS, and then see if you actually get the terms that you are missing, or are you getting some completely unwanted terms. And in this case, for all of the examples we see, it is the case that we exactly recover the piece of the OP coefficients that we are missing. So once we have this general formula, we can go step by step and consider the bootstrap axioms and see if we are missing something, or if we are actually satisfying all the conditions necessary to have a physical thermal 2-point function. So the consistency conditions, of course, start with KMS, the periodicity, and by construction we have the KMS. And then the analytic structure of the time two-point function is again it was one of our inputs, and it's the generalized method of images captures this correctly. And then the consistency with OP is again, as I said, we can expand. There's no extra operators that appear that shouldn't be there. And then maybe more subtle condition is the regioboundedness. So all the time two-point functions we consider, we assume them to be regiobounded. And in particular, once we compute the dispersion relation, we can immediately check that the piece of the correlator, that is the dispersion relation, satisfies the regioboundedness. But also, after summing over images, we can show that this full form of the two-point function satisfies the regioboundedness. And on top of it, since we assume it, we know that the arc contributions that we are not able to capture in this way should again have the contributions of the operators in the spectrum of this theory, but for finitely many spin numbers. And then the last consistency condition that Saskia asked before is that we expect to have clustering at large distances, and this means that when we take the two operators very far away from each other in the spatial separation, we expect the correlator to first of all have its one-point function in the leading order and then decay as with respect to the Tyrman mass. And this is not something we can input to, this is not something that we can ensure in this level. So this is the only condition that we need to, every time we compute a two-point function, we need to check it if the resulting generalized method of images is actually giving us the correct clustering behavior. And if not, then we know that the arcs will compensate for it. And we can also say by the uniqueness of the Tyrman two-point function, once the piece that has the generalized method of images over the dispersion relation satisfies the clustering property, then the arcs has to vanish. Because there can only be one correlator that satisfies all these conditions. Okay, so then I will apply this formula to, again, the examples that we considered before. So in the GFF example, once we compute the dispersion relation, again, there's only the identity that is contributing, and it has a very simple form that you can see here. And then once we expand these two factors in terms of the OPE, we can see that the OP coefficient, so we don't see the contribution of the identity in dispersion relation. And for the double twist operators, we only see the leading behavior. We only see this 2, which is the leading factor in this exact OP coefficient that we were expecting to see. And so you know that the zeta function can be expanded in terms of the terms that are exponential in J, and indeed this is the contribution that we are missing. And of course, okay, so I gave you the example of delta phi equal to 1 in 4 dimensions just to simplify things. And then once we sum over the images, we reconstruct the correct OP coefficient that is given here. So we can play the same game for the ON model in epsilon expansion. So remember that the only two operators that were contributing to the two-point function in order epsilon was the identity and phi square. And here it's exactly the same. And the exact OP coefficients are given here, whereas the dispersion relation alone can only capture the leading behavior. And then once we sum over images, we get the zeta function contributions and then obtain the correct 2-point function. Yeah, so here I also briefly show you how the correlator looks when we actually perform the infinite sum. And apart from the free 2-point function contribution, the rest of the correlator looks like this. And then this we can check it by computing the epsilon order Feynman diagrams from the perturbative side. And here there's only a constant many mismatch between the Feynman integrals and our generalized method of images, which confirms the list of consistency conditions that I was giving you. And okay, so finally, before finishing, I want to point out a curious connection between the momentum space correlator and the position space correlator. So previously, people wondered. So this whole talk was about the OP in position space, and then the interesting question is to ask if we have any notion of an OP in the momentum space. And it was discovered by these two papers here that once you consider a large momentum or a large frequency limit in the momentum space correlator, indeed you can formulate a form of operator product expansion in the momentum space. And it makes sense that it is in large momentum, right? Because so here we are in the thermal setting, and in the thermal setting, the OP only is convergent in a finite radius. And if you do the Fourier transformation, there is no reason to believe that such an expansion makes sense in any momentum variable. And indeed, so this is the case, but at least if you do it in the large K form and in the Euclidean setting, then the transforming the 2-point function to the momentum space fully and transforming the thermal conformal block separately to the momentum space and constructing the OP again there makes sense. So these two operations, they commute, let's say. But the interesting point about this momentum space OP is that the blocks of the momentum space do not see the contribution of every single operator that appears in the OP. So some of the operators drop out when you transform everything to the momentum space. And the operator, so for example, double twist operators, the contribution of the double twist drop out. And these are exactly the operators that also are neglected or non-seen by our dispersion relation computation. So whatever discontinuity is missing is exactly missing by the momentum space blocks. And then throughout this paper, we use this observation extensively, and we use this connection to sometimes check our position space correlators, or sometimes get a very good ansatz of the end result of the infinite sum, so that we can actually match. And then also the interesting point is that the blocks in terms of the operators that are given by the dispersion relation, they are, at the end of the day, they don't rely on the OP expansion. So then the transformation of these things to the momentum space doesn't have to again be in this large momentum limits. So there is an interesting interplay which we didn't fully go through to the end and see the connection, but the connection is there. So for the future work, I would like to point out. And with this, I can conclude. So in this talk, I presented you this analytic frame, the Analytic Bootstrap framework that we developed for thermal two-point functions based on the dispersion relation. And then, so we showed that in the zero spatial separation, this dispersion relation formalism gives you a very strict, very general description of the two-point function in terms of the generalized free fields. And on the other hand, this can so the images that appeared in the dispersion relation in complex Tau plane inspired us to conjecture this the general form of computing the thermal two-point function in non-zero spatial separation. And this is the generalized method of images method that we developed, which also works in the non-zero spatial separation. And this dispersion relation has a direct connection with the momentum space OP. And for the future directions, there are many interesting directions to go. So of course, one of them is to actually refine or apply this formalism that we developed to the holographic settings. And then see what we can compute from the boundary point of view in terms of the correlators by using this formalism. Another direction is to do this when there are defects in the thermal cylinder. And of course, we also want to do this for fermions, for fermion two-point functions. And on top of this finite temperature, we should also add the finite volume and try to develop an analytic framework also in the finite volume. So with this, I conclude. So thank you for listening.